When are we retaking this test?
This one?
Yeah.
I'll just leave it open for 2 weeks. Yeah, and I'll give you some days built in to do it. All right, so let's first of all, what are we always going to do on homework? Hopefully, but on tests for sure. What are you going to do with these drawings? Draw them and mark them up, right? Use lots of paper. Okay, so Alec, what can I do here to summarize this information? Line CD is the perpendicular bisector of segment AB. What marks can I put on there to indicate that? Okay, I can put congruent marks. Where? Okay, so there and there, right?
Yeah.
Okay, because I know that it bisects, the line bisects the segment, so it cuts it into two pieces. How do I show that it's perpendicular? Okay, good. I'm going to make it a right angle sign. Okay, there it is. That summarizes everything, right? Now, what's our relationship here? The perpendicular bisector theorem is what it's called. I don't care if you know what it's called, but I want you to know what it does. If a point is on a perpendicular bisector of a segment, what's always true about that point? So what's true about point C? Okay. True, cuts it in half, but how is specifically point C? What is point C? What's unique about that?
So it's equidistant from AB.
Good, it's equidistant from the endpoints of the segment, right? So then this is true. That's congruent to that, right?
Yeah.
Now, what I want you to think about here is what would happen, and kind of play this movie in your mind. What would happen if I were to grab point C, like in Geometry Sketchpad, and drag it up or drag it down? It's going to change, right? The position, like what if C were there instead? Well, then if that's its new position, it's different, but wouldn't you agree that those distances would stay the same? Right? They stay equal, right? Does that make sense? So then when they ask us for the relationship between AC and BC, what's the answer? Those distances. The distance AC is equal to, right, AC is equal to BC is what I would write there. Because they always stay equal, even if I drag this point along the bisector, right? Okay, questions? Okay, I think we're getting this. This is good. Okay, same deal. What about this one? What about AC and AB? Is there a relationship there? If there were some predictable relationship, when I drag C along, both of those distances should change to keep the relationship intact, right? Does that make sense? So if I drag point C again, let's say we drag it down again like we did last time. So we're going to move point C down to there. So that distance changed and that distance changed. Those are congruent. Did AB change? Stayed the same, didn't it? So can there be a relationship then between AB and AC? Look, AC got smaller, but AB didn't. How could they be connected then? Right? Whatever relationship they had before has been destroyed if I changed one of them but not the other, right? You get that?
Yeah.
So what's the answer? NA. Yeah. Really, the only relationship, there's only two that we really know here, aren't there? We know that the one we talked about, from the perpendicular bisector theorem, and then also we would know that just because, maybe there'd be an easy one that pops up, like AD and BD. Well, obviously those are congruent, right? So those would be equal, just because this D is the midpoint of the segment, right? So that would also be true. But that's really the kind of stuff we're looking for here. Okay. Okay, what about this now? We covered this. I can't remember if we covered this or not yesterday, but if we did or didn't, let's take a look at it. So tells us that ray BD is the angle bisector of angle ABC, the big angle. Okay. So what do we know about that? Well, first of all, what does that tell us? Just that statement right there. If it's the angle bisector, what marks can I put on the drawing that say that? What does it mean to bisect anything with an angle in this case? Okay. Okay, what do you think, Maisie?
You make the angles congruent.
Okay, so those would have to be
Yeah.
congruent, wouldn't they? Because the ray is cutting this big angle in half. It's cutting into two equal pieces, right? Or two congruent angles. So what's that tell us right away then about x and y?
They're equal.
They're equal. Yeah, that's the answer, isn't it? Okay, that's kind of a freebie. Maybe a harder question though would be, what if x and y were like here? Okay, what if x and y were there, for example? What's that relationship going to be? Well, what is the angle bisector theorem? It's very similar to the perpendicular bisector theorem. What it says is that if some point, call it D in this case, if some point is on an angle bisector, then that point is always equidistant from the two sides of the angle, right? So that tells me that that is congruent to that always. What if I slide the point D? It doesn't matter. If I slide the point D back to here, yes, they're both going to change, but they'll still stay congruent, right? Does that make sense? So that's the corresponding relationship that we had in the last one for an angle bisector. Okay. What if we asked about like the distance AB and AD? No relationship, right? Does that make sense? Okay. AB and AD, they're obviously, we might make them look similar, but they're never going to be, there's never, I mean, that's not what the theorem tells us. Okay. Make sense? Okay. So that would have been an NA. Oops. All right. Okay, quick review of this. Remind me from yesterday, if we know that D, E, and F are the midpoints of the sides of a triangle, then what do I call segment EF? What's that called? What's the segment that connects two midpoints of a triangle? Mid-segment. Good. If this stuff isn't making perfect sense, let me have it. Why don't we take all your, let's just put phones and earphones and all that stuff away. If this isn't making perfect sense, something I would strongly recommend, even if you think you have this stuff pretty well down, sometime between now and Thursday when we test, go back and click through the PowerPoints or take a look at the textbook, whether it's online or if you have a textbook. Either way, you have to read the whole thing, but go back and look at the definitions, look at the theorems, maybe glance at the examples. That's very helpful to do. So yeah, this is a mid-segment, isn't it? Now, what are the properties of a mid-segment? So mid-segment EF is what? Okay, so it's parallel to the other side, right? Okay, so those two are parallel. And then what else is true about the lengths? Good, it's equal to half the length of the other side, isn't it? Because the mid-segment is actually congruent to the two parts that make up the other side, that are broken up by the midpoint, right? So then, what about this case here? What are they really asking for? What does that say? Read to me in English what that says mathematically. What's that say? Justine, what's that say right there?
Segment EF.
Good, segment EF is parallel to blank. So what are they looking for here, a number or a thing? Thing, yeah, it's something that we would draw, right? Segment EF is not a number, it's something I have to draw. So what is that parallel to? So, but how would I say it? Segment, good. So I could say something like segment AB, or segment AD, or segment BA, or whatever. Any of those would work, right? Say it again.
I was just asking if either would work.
Yep, they should all work. Yep. Okay. And if they didn't, for whatever reason, just flag it and show me, and I'll give you credit. Okay. But I think they all do. Okay, this time, this last one maybe we'll look at here. What do we got? We want to know what's the length of NO. So let's highlight these here. So NO, we'll do, that is blue. So that's down here. Okay, the length of NO is negative 8x plus 10. They tell us the length of XZ, let's make that red, is negative 5x plus 3. Now, what's our strategy for dealing with a problem like this? We're supposed to find the length of a segment, so that's a number, isn't it? Right. We're going to fill in a number. How are we going to do that? Okay, we're going to set up. You're right. I mean, we're going to do some kind of a relationship, aren't we? But in order to find out what the length of NO is, what do I have to be able to do to this equation up here? Say it again. Okay, true. And you guys are you're thinking about this, but you're already thinking more complex, or you're thinking about the specific relationship. But just kind of generally speaking, in terms of a strategy, I'm going to have to somehow find the value of x, aren't I? And then plug it back in, right? How do I find a value of x? Well, I've got to set up an equation so I can solve for x. Now, what's the geometry relationship that's going to work here? NO is going to be, how's that compare to the length of XZ? It's half as big, or another way of saying that, so we don't have to use a fraction, would be to say 2 times XZ would equal the longer blue segment, right? Does that make sense? So here's how we're going to do this then. 2 times that equals that. Okay? Right? Now we just do algebra. So it's, yeah, we distribute the 2, and that gives us, would you agree, it's what, negative 10x plus 6 equals negative 8x plus 10? Now be careful with this. Danny, which direction am I going to push the variables here, preferably? They'll both work, but what's the best one?
Minus 8x.
You mean adding 8x? Okay, that, I can see why, it's going to work. That's going to give me a negative number of x's, though. What's actually bigger, negative 8 or negative 10? Negative 8's greater, isn't it? So we want to push the variables to the side where we already have more of them. So even though it would work the other way, just so we don't have to divide by a negative, let's go ahead and add 10x to both sides to move the variables to the right. So what's that mean I do to the numbers then? Move them the other way. So subtract 10. And then we should cancel 1 from one side. So variables from one side, numbers from the other. And what do we get? Negative 4 equals, that's a 10, right? So 2x. Last step? Divide by 2. So x equals what? Negative 2, right? Negative 4 divided by 2. So if I plug negative 2 in up here for x, what do I get for the length of segment NO? Negative 8 times negative 2 is 16 plus 10, 26. Right? Okay. Real quick, this probably, actually, we didn't look at this one either yesterday. Probably not a bad one. So what do they tell us here? They tell us JK, segment JK is perpendicular to segment KL, so that's a right angle. They're telling me that the measure of angle J is 54 degrees, and they want to know the measure of KSR. So they want to know the measure of this angle right there. That's kind of a tricky one a little bit. So how are we going to relate those two? Trevin, you have an idea?
KRS is the same angle as KJL.
KRS is the same, okay, good. There's a good way to do it. So we've got to find, now I know, look at this triangle down here. It's a right triangle, right? So I know that these two angles, the two acute angles, are what? What do they have to add to? 90, because there's 90 degrees right there, right? So we know the sums of the measures of the two acute angles in a right triangle are always 90. They're complementary, right? So can we set up a relationship that's going to make this angle show up in this triangle so we can find the other one? We can. What are the kind of things we could look for? Well, this is really a case where we're trying to find like maybe parallel lines cut by a transversal kind of a thing. You told me some stuff earlier about the relationships between the mid segments and the sides of a triangle. So for example, if we take this mid-segment right here, that mid-segment, because it connects points R and S, which are midpoints of sides, is parallel to what side? JL, right? So how about if we extend both of those and treat those as two parallel lines? Right? We get parallel lines. And then what might be a useful transversal if we want to find an angle that's congruent to 54? The transverse is going to be a line that cuts across both of the parallel lines, right? Yes, what about JK? Let's make this the transversal, right? So if that's the transversal, then what's the relationship between this angle and that angle? And let's just ignore, and we can do this, let's just ignore this line completely, because it's not even, it's just kind of confusing things, right?
Corresponding.
Yeah, they're corresponding angles. If parallel lines are cut by a transversal, how are corresponding angles related? They're congruent. Very good. So then we can fill in some stuff, can't we? Right? So now we know, oops. So this must be, oh gosh, it's not quite gonna work. So this is 54. So what's that one gotta be then? Well, whatever, I mean, what am I gonna subtract 54 from? 90, yeah, so 90 minus 54 is what, 36? So 36 is the answer. See how that works? Okay, once again, what made this possible? This would have been hard to do if I didn't draw on the picture, right? Drawing on the picture is so important in geometry. Okay. All right, moving on. Okay, so maybe we can probably skip this one. That's an easy one. We did that one yesterday. Okay, scalene triangle. Real quick, if I want to come up with the lengths of the sides of a scalene triangle, I just got to find any three that would work. There's an infinite number of possibilities. What does it mean to be scalene? Three different side lengths. Okay, so Brady, get me started. Listen, please. Say it again. 12. Give me another one. 12 and 3. Okay, there's two of them. So she gave us two side lengths. 3, 12. Now we want a third. Here's where we got to be a little bit careful. What's one that would work? Does 5 work? Why or why not? It's too small. 5 does. Let's look at some candidates. 5 doesn't work. I heard 16. Does 16 work? What's the problem with 16? 3 plus 12 would need to be bigger than the other side, and it's not, right? So that doesn't work.
Then why wouldn't 5 work?
Okay, 5 wouldn't work. Listen, please. Remember what the triangle inequality says. The triangle inequality says that when we're trying to pick the side lengths of a triangle, there's one rule that we always have to follow. The sum of the lengths of any two sides has to always be greater than the other side, right? And so what we can always do if we have numbers up there, it's pretty simple. We just know that the two smaller ones then always have to exceed the one bigger one, right? So what's the problem here? 3 and 5 only add up to 8, right? They need to be, the two smaller ones have to add up to something greater than the bigger one.
Yeah, but 3 plus 12 is 15.
Okay. Okay, so let's try those. 3, 12, and 15. Does that work?
Okay, so it has to work all the way around.
It has to work all the way around. So what's an answer that would work? 14. 14's fine, right? That makes sense. They're all different side lengths, and the sum of the two smaller ones is greater than the other one, right? Right, Maisie?
Yes.
Okay.
Oh, okay.
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 We good?
That had to be smaller.
Questions on that?
I'm okay now. What about a right triangle?
Okay, let's do one like that.
Okay.
More than 12
Two smaller sides need to be greater than
So 10 was, 10 plus 3 is 12.
Okay. Okay, look here, please. Get everybody facing the front. Everybody focus up here. I want everybody's, watching what I'm doing. So this is not on the test, but it's on the homework, so you gotta be able to deal with this. What would we do if we want to enter the lengths of three sides that would build an obtuse isosceles triangle? Now that's a little more specific. If it's isosceles, what does that mean? Two sides have the same length. I'm going to make a recommendation. Don't choose side lengths like 1 and 1 or something, because then it really limits the number of available whole numbers you could use for your other sides. Pick numbers that are a little bit bigger. Like let's pick, I don't know, like 10 and 10 or something big. Okay? So what if we do that? And those are easy numbers to deal with. What if we pick numbers like 2 of them need to be the same because it's isosceles. So isosceles part gives us 10 and 10. Now what about the obtuse part? Okay, the obtuse part means that the other angle, the other side needs to make sure that the biggest angle in the triangle is bigger than 90, right? Does anybody have a strategy for this? How we could do this? Okay, a really big side. How do we make sure that it's big enough?
Put it just under what the 2 more equal.
Okay, so let's take a strategy where if we could figure out what the side length would be necessary to make a right triangle, we could just tweak it a little bit, right? Now, what's probably the most famous theorem in all of math is the one that tells us about the relationship between the side lengths of a right triangle. What is that? Pythagorean theorem, right? So we know that in a right triangle, if the legs are A and B and the hypotenuse is C, that's just the one that says A squared plus B squared equals C squared, right? So if we want to find out what the other side length needs to be, well, let's just call it, how about if we just call it X? So we got a 10 and a 10, and let's call it X, right? So then that means that X squared would have to equal 10 squared plus 10 squared if we wanted it to be a right triangle, right? So that's 100 plus 100. So X squared would equal 200. And so if I square root both sides, X is equal to the square root of 200, which is about 141 point something. 14 point something. 0.1 something. Sorry. So, yeah, 14.1 blah, blah, blah. That would be the exact length that we need to make a right triangle. But if we want to make it obtuse, what would I have to do to the length of that side? So if this is my right triangle, it's 10, 10, and about 14.1. What would I have to do to this side to make this angle bigger than 90? Make it bigger, right? Because big sides look at big angles. So give me an example of a side length that would work. 20? Well, no.
17.
17 would work. 20 wouldn't work because 10 plus 10 has to be more than the other side, but 17 would work, right? Or 15, or 19, or 18, or 17.1 if you want to use a decimal. Yeah.
Couldn't you just add up some 2 numbers here that equal, just put it a little bit below that? So
Yeah, I mean, you probably could. You probably could add them up, but what if one of those numbers, I'd say where that could fail
I know,
is,
I'm just talking about this problem.
yeah, for this, you're right. I mean, you probably could get away with that, yeah. Okay, but this is in general how you would do it for every, does that make sense? Okay.
That's nice.
All right. Okay, I think, yes or no, do you want to go through this one? Raise your hand if you want to go through that one. I think we did that yesterday, but I'm happy to do it again. Okay, let's take a quick look.
I just said no.
No, I know, but there were a few people that wanted to, so we'll do it real quick. So XY. Once again, get everybody facing up here, please. Okay. So they give us two sides, XZ and YZ, right? So I've got to find, potentially, I know that probably I'm going to be limited to what's the smallest value I could pick for the missing side or the biggest value, right? Probably the easiest way to think about this would be think about it kind of in 2 steps. What would happen if the missing side what if XY is longest side? If it's the longest side, then what would have to be true? The other two sides would always have to do what? By the triangle inequality. Good, they have to add up to more than it, right? The two smallest lengths have to add up to more than the biggest length, right? So the smallest lengths, 6 plus 10, would have to be bigger than XY, right? Okay, so what if it's not the longest side? That's the other possibility. XY is not the longest side. Then which one is?
10.
10, right? So then what would have to be true? 6 plus what?
5.
Well, plus XY,
Oh.
right? We don't know what its length is yet, but 6 plus XY would have to be greater than the biggest side, which is 10. Does that make sense? So those are the two conditions that have to be true if it's going to obey the triangle inequality. So we'll just solve both of these and see what we get. Well, how do I solve this one? 10 plus 6. So this gives me 16 is greater than XY, or another way of saying that is XY is less than 16. What about down here? How do I solve for XY? Subtract 6. And I get XY is greater than 4. So I've got to say both of those two things combined. Oops. So if XY is going to be bigger than 4 and less than 16, we can write that as a compound inequality, right? We always want to put like a number line, the smaller number on the left, bigger number on the right. So XY is greater than 4 and less than 16 is our answer, right? That's a very informative way of writing it. It tells us what the boundaries are, and any value in between is okay. Questions? Okay. Yep, you bet. Okay, we did this one yesterday. I'm going to skip this one. Triangle inequality. We did this one. How would I, if I want to find the shortest side, what would I do? Just in general?
Find the 3 angles and
Good.
the smallest angle opposite side is the shortest side.
Good, yeah. Fill in the 3 angles. Whichever angle is the smallest, the opposite side's the answer, right? That's the shortest side. And then, similar to that, if it asks me sort of the opposite question, if it gives me the 3 side lengths and I want to find the largest angle, which one's that going to be? In fact, we can do this one real quick. If FT is 24, FC is 22, CT is 21, what's the biggest angle?
Angles.
Angle C, right? Because that's opposite the longest side. Okay, so angle C, check, got it. Okay, now we're on to last stuff. This is 5-6, and this is it. This is the rubber band stuff, right? Okay. So the hinge theorem. So if they're telling us that the measure of, what are they telling us here? They're telling us that the measure of BC, okay, let's fill this in. The measure of BC is 18, and the measure of DF is 16. Can we determine which angle is bigger, 1 or 2? 2. Looks like 2 would be, right? But what's the problem with that? We haven't quite met the conditions. This isn't really a hinge theorem problem. What's the problem?
We only have one congruent side.
Yeah, we only have one congruent side. Think what this means, right? The hinge theorem is where, mathematically, what the hinge theorem says is if 2 sides in one triangle are congruent to the corresponding 2 sides in another triangle, then the included angles become the hinge angles. Thinking about that in terms of like boards and rubber bands. If I've got these boards have the same length, and these boards would have to have the same length also, right? Then we can compare the lengths of the rubber bands by looking at the size of the angles, right? But we don't know that those sides are the same length, do we? So I could distort this. This is really the same thing as saying, let me just do this. I could change this in this way. I could make this top triangle look like this, for example. AB has to be congruent to EF. Let's just say hypothetically that those are 20. So here's AB, it's 20, right? But AC might only be, I don't know, let's say that it's 10. So AC could be really short. Actually, let's make it long. Let's make it 30. So let's make it really long. Yeah. Oops. Or, yeah, 30 is fine. So then this thing would look kind of like this, right? And what if this side over here is really short? Let's say this side is only like 1. Then we've got a side up here that's 20. We've got a side that's only 1. And then this side has got to be really long. See what I'm saying? It doesn't look like it's supposed to, right? We don't really know how the angles are going to be related because these boards were different lengths. We have to have 2 boards that are the same length with a hinge attached between them, right? Does that make sense? So what's the answer here? There's not enough information because we don't have 2 pairs of congruent sides. We've only got 1. Right? So it's not a hinge theorem thing. You gotta have 2. Oops. Okay, well, this one is a hinge theorem problem, isn't it? Because now I've got the blue sides are congruent, and the red sides are congruent. Oops. The red sides are congruent. And they tell us that the measure of angle C is 105, and the measure of angle F is 108. So what must be true of the rubber bands then? Which rubber band has got to be stretched longer? Yeah, DE's got to be longer, doesn't it? Right? So that's got to be true. Make sense? Yep. All right, what about this one? Fill in the blanks here. So it's telling us BD equals 23 and BC equals 23. So those are going to be equal, aren't they? Those lengths are equal, so they're congruent. Any other congruent sides in the 2 triangles?
Shared side.
Shared side. Yeah, they share this side BA, and so that board in each triangle is the same length. So then that means that these must be the rubber bands, right? What do they tell us here? They tell us that the measure of angle DBA, so the top one is 65, and the bottom one is 64. Okay, so AC is equal to X, and AD is equal to 22. So what has to be true here? What does the hinge theorem tell us about this?
X is less than 22.
Yeah, this has got to be a bigger rubber band length, right? So we know this is the smaller one, so X has to be less than 22. If you put that down, you're going to get partial credit because that answer says that X could be any number less than 22, like negative a billion. Does that work?
Greater than 0.
It's got to be greater than 0, right? Because this is a side of a triangle, and so it has to be some positive number. So we have to combine that result with the fact that X can't be 0 or negative. So how would I say both of those combined? X is greater than 0 and it's less than 22. What would I say there? How would I do that? How do I write that as a compound inequality? Molly, how do I write that as a compound inequality? It's gonna be greater than 0 and less than 22. What do you think? We can do that. Somebody help us out here.
Is less than 22.
Okay, so it's gonna, I gotta do a less than 22, so the big number goes on the right,
And then, the one that goes is
greater than
0.
0, right? So kind of, how do we get there? We always know that x is in the middle, the smaller number goes on the left, the bigger number goes on the right, and then I just keep these relationships, right? So I probably would start like this, x, 0, 22. How is x related to 0? Well, it's gotta be bigger than 0, and it's gotta be less than 22, right? Okay? Alright, we're almost there. Last one, how about that? Last one. Okay, what about this? So what do they tell us here? AB is equal to BC, so let's make those blue, right? So those sides are congruent. AE is equal to CE, so those sides are congruent. All right, so what does that tell us about the rubber bands then? What do we know? They share the same rubber band, don't they? Right? Everybody see that? So if they share the same rubber band, Cassidy, what's going to be true then of the angles in the middle if they share the same rubber band?
X equals, those angles, yeah,
So, yeah, what are you going to say?
X equals W.
That's it. X equals W, right? Because if this is the same length, then the angles opposite that side have to be the same angles. Very good. So the answer is just X equals W. Good job. Okay, does that make sense? Okay. All right. How much time we got? 5 minutes. If you want to jump on there, you can, but it's up to you. But I'm tired of talking.